All right, hi everyone. I'm going to be talking about problem F from Codeforces around 734 right now. So hopefully I do a good job of that. All right, so once again, I'm going to assume you've read the problem. If you haven't, then go ahead and read the problem. I put the link in the description down below. Okay, so we have basically have an undirected tree and a number k. So I'm just going to draw a sample out here because I think that's the easiest way to understand this. So I'll take n is equal to 5, k is equal to 3, and our tree could look something like 1, hold on. Our tree could look something, okay, so this is node 1, this is node 2, 2 goes to node 3, 2 goes to node 4, and then 4 nodes to go to 5, node 5. Okay, so let's assume we have a tree of size 5 and k is equal to 3. Basically, we want to count the number of subsets of nodes such that the size of a subset is equal to k, and the pairwise distances between all nodes in the subset are the same distance. So let's just dissect the problem a little bit and think of kind of some special cases. Hold on, my camera is weird. Okay, I think it's better. So what if we assume k is equal to 2 in any tree, no matter what? Well, the problem defines a k element subset to be valid if between every distinct pair of nodes, their distances are all equal. Well, the thing is if k is equal to 2, there's really only one pair that exists in the first place. So no matter what the distance between this pair is, between these two nodes, it's always going to be the same because it's just one distance value. So what this means is that if k is equal to 2, our answer is always going to be n times n minus 1 over 2 because we have n choices for the first node, n minus 1 choices for the second node, and because these are unordered pairs, we don't want to count AB and BA twice. We just want to count this once. We divide everything by 2. So this is the answer if k is equal to 2. All right, now let's assume k is not equal to 2. In other words, let's assume that k is greater than or equal to 3. So if k was greater than or equal to 3, then we have to be a little bit careful over here. And I think this is better to illustrate if we look at this example over here. So in this case, there's only one subset of size 3 that satisfies this condition, and that's if we take node 1, node 3, and node 4. So I'll draw in the nodes that we take in. I'll draw them in as black. So we took node 1, we took node 3, and we took node 4. As you can see, the distance between this node and this node is 2. The distance between this node and this node is also 2. And the distance between this node and this node is indeed also 2. So that's why this is a valid subset. All right, so let's first try to think about subsets of size 3. Because one important thing to notice is that if we have a subset of, let's say, I'll just randomly draw. Hold on, how do I explain this? Okay, I'll do it like this. Let's say we have a subset of 4 nodes, or like 5 nodes. Yeah, let's just say we have a subset of 5 nodes that are all the same distance to each other. And the easiest way to represent this is if we have a star like this, where the black nodes are nodes that are included in a subset. So if k is equal to 5, or like the size of this valid subset is equal to 5, notice that a smaller subset of the set that we chose also has to be valid. In other words, if the subset containing all 5 of these vertices constitute a valid set, then that means that if we remove any one of these black vertices, the remaining 4 vertices will still constitute a valid set. And that's because we didn't add any new pairs into this smaller set. All we did is strictly remove pairs. And if our set of pairs have the same distance before, and we just remove a few of those pairs from the set, the remaining pairs still have the same distance value, so it's still a valid subset. And so we have 4 nodes they have like a 4-node subset that we generated from the subset of 5 nodes. And then in turn, if we remove like any like another random node over here, this is still a valid set of 3 nodes. So this observation is important because it allows us to find the property as to what a valid subset looks like in the first place. And so let's do that right now. So let's first focus on subsets of size 3, because any valid subset of size greater than 3 will always contain a subset of size equal to 3 as a subset of this original set, because of a logic that I just mentioned. So let's just say we have 2 nodes already decided, like 2 nodes that we want to include in the subset. So like, for example, we just have some nodes here and just they're connected by some chain of nodes and they go over here. So this is node A and this is node B, for example. So, okay, this is not that good of an example. Let me just remove one node in here. Yeah, okay. So let's say that we want to figure out where the 3rd node could be located. The 3rd node, one thing to notice is that there could be some nodes extending from A, some nodes extending from B, it doesn't really matter. But the thing is that if we consider this side of the tree to be a subtree of A, and this side of a tree to be the subtree of B, the 3rd node, which we can define as node C, cannot be in either one of these subtrees. And the reason why is because if node C was in the subtree of A, it will always be closer to A than it is to B. And because of that, the distance from A to C would never be equal to the distance from C to B. And this would violate the property that we're trying to satisfy in a good subset. And the same logic applies if node C was located in the subtree of B. Okay? So that's kind of one thing we can point out. And another thing we can point out is that if we look at where we can choose wherever node C is located, we can only really put it in one place, because we know the distance from A to B is in this case equal to 1, 2, 3, 4. We know the distance from A to B is equal to 4, which means that this also has to be equal to the distance from A to C and distance from B to C. So what this implies is that the distance from A to C has to equal the distance from B to C, which means node C has to be located somewhere in the middle of a path from A to B. In other words, we can't choose this node as C because it's closer to A than B, and we can't choose this node as C, and we can't because it's closer to B and A. And we can't really choose a node that's in this subtree of this node or the subtree of this node. The only option we really have is if our tree looked something like this, and the black node is node C that I conveniently put over there. Wonderful. But anyway, this is really the only other choice we can have for node C, because we have node A and node B. This distance is already defined, so we have to notice that whenever node C, we start from node C and we travel, keep on traveling these nodes until we hit this line over here. The node that we hit in the line has to be exactly in the middle of a path from A to B. And also on top of that, we know that because it cuts in the middle, this distance over here is equal to this distance over here. So in this case, this distance is 2, and this distance is also 2, and they have to be equal. And because we know that distance from A to B is 2 times 2, which is equal to 4, we know that this distance over here is also equal to 2. So this right here is the important property that we're trying to figure out in the first place. We can reword the condition of k element subset of a good subset like this. Notice that in this example, This node right here, hold on. Let me just, how do I, okay. This node right here is essentially a center. So what I mean by the center is that like the distance from A to the center is 2, the distance from B to the center is also 2, and the distance from C to the center is also 2. So so this allows us to motivate the following solution. Let's first like iterate over all possible centers, and there's obviously n of them. So let's assume that we just have like a random tree. In this tree, we, at least for now, we root it at the center over here. Let me see if I have something like this. Okay. So let's assume our tree looks something like this. And we want to have k is equal to 3. So we want to choose, or we want to count how many subsets of size 3 exist that are all the same distance from a center. And on top of that, we also have to make sure that for all nodes that we choose, so like let's say, for example, like this is our center over here, and this is like some arbitrary node that we choose. We also have to be careful in that the LCA of this node and any other black node that we choose has to equal to the center node in the first place. Because if the LCA of like 2 black nodes that we pick is not the center, then that means it would look something like this in the tree, where like this would be the LCA, and like this would be like a black node, and this would be like a black node over here. And the distance between these 2 black nodes would not be equal to the distance from this black node to the center. And that's because we essentially have like this overlap of a path that like gets cut out, and it wouldn't be the same value, right? So that's a condition that we have to be careful about. So the way we can implement this is actually somewhat similar to, I believe, Codeforces round 728 2D/1B. I think it's similar to that problem, yeah. So basically what we do over here is we want to say, okay, well, a valid subset would have, we would make sure that the common LCA would be the center over here. Or like, by common LCA, I mean like LCA of any like pair of black nodes. So for example, this over here is one valid like subset, right? If we just choose all nodes in this layer over here. Another valid subset is if we choose like this node, and this node, or we can like choose like this node, and this node, like so over, whatever. It doesn't really matter. What matters is that 1, the distance from all black nodes to the center is constant, and 2, for every like subtree that we defined in here, it's like we can say if this is center, then these are all like child subtrees. In all of these child subtrees, we want to choose at most 1 node to be black from each subtree. And that's how we can guarantee that the LCA between any 2 black nodes will always be the center. And so from here, it's, we can do a DP. We can kind of like, yeah, we can basically do like a DP logic. So for every center that we choose, we want to first do a BFS or a DFS to compute the depth of every node, as well as which child subtree that node is located in. And by child subtree, I mean like the subtree, like which child subtree is it in, where the child is a direct, is a direct child of the center. Can we still see that? Let me kill. We can. Huge. Okay, so one way we can do this is, let's assume we have like the depth. We have the depth of all vertices, and we also have basically the subtree. I'll call it ID of a node V. And obviously, we don't really care about the depth or the ID of the center itself, because it's not a node that we will ever include in the subset. It's simply just a kind of representative node that we can use to define a valid subset, but it's never actually part of the subset. And so what we can do is, we know that the depth of all nodes that we can include in a subset has to be constant. So we can iterate over this. So iterate over all depths. And so for all nodes that are like of a depth equal to D, we want to count how many nodes have like a certain ID value. So what I mean by this is, let's say this is our center of our tree. And we have, in this case, if the center of a tree had 3 children, we would have 3 different IDs. Where like this is like the subtree of this node, the subtree of this node, and like a subtree of this node, whatever. It doesn't really matter what the actual contents are in here. It just matters that we have 3 different subtrees. So for each depth, let's say we want to check like D is equal to 2, and we have 2 nodes of depth equal to 2 in this first component. We have 3 nodes of depth equal to 2 in here, and we only have 1 node of depth equal to 2 in this subtree over here. And if, for example, if k was equal to 3, we have to count how many ways can we color these nodes to be black such that we have exactly 3 black colored nodes, and in each of these subtrees we chose at most 1 color. And so in other words, we have like 2 choices from this first subtree, but we can never take both of these nodes because then that would violate the good subset property. And so we have like 2 choices from this subtree, we have 3 choices from this subtree, and we have only 1 choice from this subtree. But if we choose to color a node from any of these subtrees, this will only increase the number of nodes in our current subset by at most 1. So we can have a DP where it's like DP at, I guess, how do I say this? DP at I is equal to the number of ways to obtain valid subset of size I. And we can kind of implement this DP with like, it's kind of like how a knapsack DP works when you're also you're counting like a number of ways to do it. So refer to my implementation if you want a little bit of a better idea of what I'm talking about. But basically what we're doing over here is that we can actually, this is technically a 2-dimensional DP, but we can only use O of n memory if we carefully define this DP. So DP at I, that's not an I, that's a V. Okay, that's a little better. So DP at I will be equal to essentially DP at I minus 1, right? Times the number of ways we can pick a node from this current subtree that we're considering. And so this will increase the number of subsets of size I that exist in the first place. And so if we iterate over like these DP attributes carefully, and ways is just like, in this case, ways is equal to 2, and for this first subtree, and then the second subtree, ways is equal to 3, and then the third child subtree, ways is equal to 1, like whatever, we can actually determine like this DP value at the end. And after we process all of these subtrees, DP at k will be the number of k element subsets, such that like number of k element subsets that are defined by this current center over here. So basically for every center, this DP over here will run in n times k time, and we have to consider all centers, and there's a total of n centers in total. So the complexity will look something like n, because we have n centers, and then for each center we do an n times k DP that calculates our answer. So n times k, this is O of n squared k complexity, and because n and k are at most 100, this is basically at most 10 to the 6 operations, which should easily run in time. So yeah, this is how we approach problem F from Codeforces round 734. If you have any questions, then leave them down in the comments and I'll try my best to get to them. Other than that, I hope you have a nice day. See ya.